All right, Bergson and the holographic theory of mind, part 45D in the quantum series, continuing on from the black body of 45C, the photoelectric effect, where supposedly the wave theory of energy transmission and the ether that supported the waves were totally destroyed. So the photoelectric effect is from the quantum mechanics story, just photons, no waves. And we'll see the math works, but we're going to see a bit of blurring. Where is and where did wave intensity actually go? Then we'll look at Kessler again, Jacob Kessler, and the wave explanation, shot at the photoelectric effect, defending the observations on the photoelectric effect and the cutoff frequency problem, which is a problem. And then, oh, what the heck? Because there is, in fact, a wave explanation, fully accepted, Lamb and Scully. And we'll see what this does to the quantum story. There's a bit of a crumbling involved. The standard recounting of the classical to quantum transition, as I noted last time, is Einstein's explanation in 1905 of the photoelectric effect that holds center stage. This is where the photon was born. Well, actually, it was a term coined by Compton in 1927. This is where Planck's concept of quanta was actually realized, utilized, made effective, more concrete. This is where the wave theory of energy transmission with its ether medium was destroyed. Ether not needed. Merely add in special relativity, which also appeared to make the existence of an ether unnecessary. But how good is this explanation? Was the wave theory really destroyed? The wiki entry on the photoelectric effect is curious. To quote, in 1905, Albert Einstein solved this apparent paradox by describing light as composed of discrete quanta, now called photons, rather than continuous waves. Based upon the Max Planck's theory of black body radiation, Einstein theorized that the energy in each quantum of light was equal to the frequency multiplied by a constant, later called Planck's constant. A photon above a threshold frequency has the required energy to eject a single electron, creating the observed effect. This discovery led to the quantum revolution in physics and earned Einstein the Nobel Prize in Physics in 1921. By wave-particle duality, the effect can be analyzed purely in terms of waves, though not as conveniently. A wave explanation works? By wave-particle duality? Really? The fishy sensor should activate here. And what is that reference of 48? 48 is this: the photoelectric effect without photons. Willis E. Lamb, Yale, Marlin O. Scully, MIT, 1961, I believe. Starting as a misconception which most physicists acquire in their formative years is that the photoelectric effect requires the quantization of the electromagnetic field for its explanation. So remember, in our electromagnetic field, EMF, our wave form with the magnetic field orthogonal to the electric field, which we've had some discussion about. And this is going to be quantized. We're going to turn it into bullets or photons, bullets of energy. And it is an historical accident that the photon concept should have acquired its strongest early support from Einstein's considerations on the photoelectric effect. Finally, in conclusion, we understand the photoelectric effect as being the result of a classical field falling on a quantized electron. The introduction of the photon concept is neither logically implied by nor necessary for the explanation of the photoelectric effect. Lamb and Scully do say the field needs to be quantized for some effects. They note the quantum effect, spontaneous emission, the black body, and which we've looked at, and electrodynamic shifts. These effects are yet other questions, as we've seen with the black body, but definitely not for the photoelectric effect. There's no need to quantize. So these guys we'll save for a bit later. But I'll note, nowhere in their explanation is invoked particle-wave duality. This is a wiki smokescreen. I would just note it seems that wiki felt compelled to acknowledge Lamb and Scully, despite the PE as the definitive origin of quanta story. So we're going to look at the PE as given by a physics explanatory vid with the usual worship of the photoelectric effect as the origin of QM. And then we'll see at least the consideration of what an ether wave explanation would look like, more considerations of things that seem to be missing. And then we'll come back around to Lamb and Scully. The Doc Schuster channel has a 2013 video on the photoelectric effect. 3 traces flow. We have an emitter right there, a collector right there, an ammeter right there for measuring current, all encased in a glass tube, a vacuum thing. And we'll need a light source. The light energy hits the emitter, bang, and there's atoms in the metal of the emitter. They have outer or valence electrons that get knocked out of orbit. Hit by enough energy, off they go, and they fly to the collector. And we'll get a current flow as measured by the ammeter. So we start to get that current flow. Doc now lays out the 2 assumptions of classical physics, or the old wave physics, which he thinks is really stupid. So there's the 2 classical predictions. I'm just reproducing his notes there. Doc does this particularly on the fly. The 2 classical assumptions. 1, regardless of frequency, that is color of electrons will be emitted if the intensity is enough. Doc writes amplitude in the figure. So intensity is equivalent to amplitude as far as he is concerned. And he proceeds to draw the amplitude difference just to the left of the 2 there, saying there's an amplitude difference. You got big amplitude waves, small amplitude waves, saying the big amplitude wave will knock off the electron more effectively than the smaller amplitude wave. Second, Kmax, or the maximum kinetic energy, gets bigger as the amplitude gets bigger. So if the wave is bigger in amplitude, we're going to emit even faster electrons from the emitter. So any given electron seems like it could have a very large amount of Ke, or kinetic energy. With a really big amplitude, we could knock out an electron with an enormous amount of kinetic energy, or Ke. Those are the 2 classical assumptions. The Doc now says, if these light waves are indeed particles, what does this even mean for these 2 predictions? And so he redraws these as such, as wave packets. And he kind of struggles with the terminology of what to even call these, because, well, they're waves, but they're packets. And then he says, you will see that these 2 assumptions are completely nuts. He goes on, if the amplitude is big enough, but if we've got particles, what does amplitude even mean? Increasing the amount of light that hits the emitter means sending more particles in. E equals h nu, he says. This means that the energy of every single particle is proportional to the frequency. So if you want more light, you don't increase amplitude, you increase the number of photons. The wave is just a string of photons, each interacting with a single electron. So for the same frequency, he's saying to increase the amplitude, just increase the number of photons. So to the right there, we have the normal depiction of amplitude, high amplitude wave, low amplitude wave, which is equivalent to high energy wave or low energy wave, respectively. Greater amplitude carries more energy. But what Doc is pointing to is that we're saying this is now all a string of photons. My little red lines there, 4 photons, or higher amplitude, but same frequency, just more photons. So amplitude is gone into the Einstein wastebasket. Now just the number of photons, with the frequency somehow contained in each photon. So somehow you've got a frequency embodied in this photon, this is truly a Zen koan at the very core, beginning of quantum mechanics. So we'll see. So the doc now says, Kmax gets bigger. That's insane. So of course he's referring here to the kinetic energy of those electrons escaping from the emitter going toward the collector, getting stronger and stronger. Why? Because you're sending the photons in and they're interacting with one electron. Again, the gray area, the gray arrow pointing to the valence electron model. If you send more photons, increase the frequency, E equals h nu, you'll just interact with more electrons. That is, Kmax will never get bigger due to more photons or greater amplitude. That is, there will be more electrons released, but they will not be going faster. That is, you will get a greater current, that is, more electrons, nothing more. So let's look at this interaction model between light and the electrons in the metal. So cutoff frequency. There's a cutoff frequency, termed F0, or higher, needed to create any current, that is, to knock off an electron off that emitter so it flies to the collector and creates current. So if it's a red light that's being emitted from the flashlights or from the green toward the emitter, well, you may get nothing from that emitter. At yellow, a yellow light being emitted, yes, you might get, you'll get, perhaps that light is enough to a frequency to knock the electrons off. At blue, you're going to get the same amount of electrons emitted as at yellow. So you have to hit the electron hard enough. If you don't, it can't get free. It's like a pit. And Doc visualizes a pit, an electron in a pit, in one of those orbits, an energy pit, shall we say. And it won't get knocked out unless with enough energy, E0, which is proportional to h nu. So bam, we hit it, enough energy in that packet, we knock it out. So no, we're hitting an electron traveling in its orbit at high speed with a bullet, a photon traveling at light speed. I find this conception interesting once one thinks about it, because it's somewhat like a Star Wars defense critique. We're hitting a missile with a bullet, another missile. The electron is flying around and the photon is flying in. What's the probability of hitting one? Just find that interesting. But in any case, this is the model of the interaction. The metal of the emitter is important. This relates to what's called the work function. The metal of the emitter is important. To dislodge an electron, each metal requires a different amount of energy, that is, work. Sodium, Na, a certain F0, again a cutoff frequency. Gold, Au, another a certain cutoff frequency for gold. The F0 for each equals the work function, or phi. That is, phi is the amount of energy E needed. So F0, the frequency, is a function of phi over h. With light, there is both pressure and intensity. It's the latter, the intensity, that's most important for the photoelectric effect. When a spherical wave from the ether in Kessler's vision strikes a vibrator particle in the metal surface, a yellow particle there, the transverse portion of the wave carries the particle with it along a radius of the spherical wave. The quantity of energy E the particle receives is proportional to the number of active ether elements in the spherical surface of the wave, in turn a function of the number of vibrators at the source of or forming the spherical wave. So you have vibrators in that light source, and they're all contributing to that spherical wave surface hitting the vibrator particle. You can have a greater number of vibrators, but the point is they're all vibrating in phase at the same frequency and contributing to the intensity of the wavefront. Things out of phase, not in the same frequency, aren't contributing to that intensity. The vibrator particle in the metal returns at the speed of light. The amount of displacement depends on the energy or intensity received. The strain or displacement is equivalent to a volume enlargement of the positive electric field of the nucleus on the orbital electrons. And now note, when you read other descriptions like in Wiki, they point to this more sophisticated version than Doc is pointing to, that is more than just the pit. The wave is interacting with the whole structure of the atom electron. The orbital electron's velocity is increased, its orbit expanded. Each source vibrator is giving off a spherical wave. Again, they're all the same phase and the same frequency. And the energies of the waves are additive, the sum of intensity and pressure. They're acting as a unit, contributing to the overall wavefront, the intensity thereof. The pressure follows the inverse square law. The pressure exerted on the surface follows the inverse square law with respect to distance. It's proportional 1 over d squared. This can be neglected. It's not an important factor. So ask this. Suppose we increase the frequency of the vibrators in the source. In fact, let's just take one frequency, one vibrator, and increase its frequency. So we get, according to quantum mechanics, increasing more energy, E equals h nu. Is this the same as increasing the number of vibrators? Well, light pressure and intensity for Kessler are falling on its surface, and this does not vary as a function of frequency, rather as the number of vibrators or waves in the wavefront at a frequency. So the wavefront, the overall composite wavefront emanating from the vibrators, all in phase. But for Doc, we just increased the frequency to increase the energy, energy being simply proportional to frequency. E equals h nu, or E is proportional to F. So yes, the math works. We get an increase of energy, but is the actual nature of the energy over frequency increase being obscured? That is, more vibrators are actually getting involved. So the answer for Kessler would be no, it's not the same. Increasing the frequency of a vibrator is not the same as increasing the number of vibrators. I guess another way to look at this is this wave packet that Doc drew. And if you heard him, he struggled greatly over admitting the coherence of it or explicating it, because you actually have a frequency embodied in a pulse. So that wave packet is an energy somehow reflective of a frequency, h nu. That is, it's an energy reflective of multiple waves and all rolled somehow into a single pulse. So is this actually a pulse propagating through the medium from multiple in-phase source vibrators in that little flashlight? Whatever the source is, it's going to emit the so-called photon. So we look at waves in the two observed laws. That is, the two things that are normally seen with this effect, not the classical predictions. Law 1, the quantity of electrons emitted per second is directly proportional to the intensity of the light falling on the emitter surface. Well, the first law is met by the wave theory. If the energy delivered by the wave per unit time is constant, the quantity of photoelectrons released will be proportional to the energy delivered per second, in turn proportional to the intensity. It is the intensity that throws the electron out of orbit. Light intensity acts in units. It's wavefronts. The frequency does not affect the action of a wavefront in an intensity. The vibrators return to their neutral centers as the next wave arrives. So the quantity of electrons released is independent of any frequency, as Law 1 states. Law 2. The energy, K, or velocity of the electron leaving the emitter, the metal surface, is proportional to the frequency of the light falling on the surface and independent of intensity. So we're getting close to it, not quite the same as the prediction that Doc noted. The second law is also met, the observed law. The vibrators are displaced and return thousands of times per second depending on the frequency. If an electron is released from its orbit via the intensity, as it escapes, it receives energy pulses from the inner shells. This, of course, is frequency related. Thus, higher frequency leads to higher energy. So, a more sophisticated, more thought through wave theory works. In other words, as Kessler was arguing, wave theory wasn't really given a chance, really penetrated its actual predictions. That is, the supposed assumptions of wave theory weren't properly examined. So let's look at the color dependency and cutoff frequency. This was Doc's first classical prediction. That is, regardless of frequency, an electron is emitted if amplitude is large enough. The cutoff frequency. This was a stumbling block for the wave theory, a problem deemed insurmountable. Again, the cutoff frequency right there in his notes. Copper, tin, iron emit only with high frequency ultraviolet light. The slightest intensity of an ultraviolet source will cause the emission of electrons. Their speed and energy will be the same as a greater intensity of the same ultraviolet light at a higher quantity of emission. Below this frequency, no intensity works. Gold will not react to visible light no matter what the intensity. The QM solution seems so simple. Given E is proportional to F, the energy is simply proportional to the frequency. The higher the frequency, the larger the quantum E. Zinc, for example, its atom is less active. It needs a larger quantum to knock it out of that little valley there. Sodium, more active, thus less E, less energy to knock it out. Thus, sodium reacts to low frequency visible light. Zinc does not. Iron, Fe, does not. So we have this kind of table here. We have the minimum wavelength for the minimum frequency required for emission, going from a low frequency to high frequency. So cesium takes a max of 12,000 AU, sodium a max of 10,000 AU, tin a max of 3,600 AU, that type of relationship. None will react at lesser frequencies. Why? For quantum mechanics, again, it's easy. Well, it's just the amount of energy imparted by given the frequency of the light, and therefore a bigger quantum. But something is blurred, the relation between the minimum frequency and the corresponding intensity that a frequency bears. It is the intensity that first liberates the electron from its little hole, and the frequency imparts or determines the velocity. there must exist an intensity at the threshold frequency. But what does this mean? None will react at lesser frequencies. Why? In any emission, we have this relationship I over Q equals K, where I is the intensity and Q is the number of electrons per second that are being released. So you have this constant ratio. Sodium begins to emit as the frequency rises to the point corresponding to 10,000 AU. But at this threshold, the emission becomes subject to the law I over Q equals K. As I increases, Q increases. The intensity, is a measure of the number of vibrators in the source, back to our green flashlight. And Q is proportional to this number. I over Q is the average energy necessary to release one electron. There must be a sufficient number of vibrators comprising the wave of frequency F to create the required intensity. The threshold frequency is the frequency attained during a progressive growth in the number of vibrators emitting that particular frequency. The differences in the atoms, gold, sodium, zinc, determine the particular intrinsic intensity required. The cutoff frequency then or threshold frequency is incidental. It corresponds to the intrinsic intensity available only at that frequency. An intensity needed to blast the electron out of orbit. Again, it's the frequency that accelerates it, that gives it its energy as it leaves. So Q, the number of electrons emitted, is proportional to intensity, and the energy received is proportional to the frequency. So this is the question: how frequency varies as intrinsic intensity varies per Kessler. How intensity rises with frequency. And this leads him back essentially to the black body and the concept of a recruitment or grouping of vibrators in the black body case via a rising temperature, and they're grouping in a frequency. And he would see the similar thing for the flashlight. Now, frankly, Kessler begins to struggle here. He sees an intensity as a function of the number of source vibrators. But say the threshold frequency is 1,000, and I have a pile of vibrators happily vibrating away at 900 frequency. Why not simply add vibrators at frequency 900 until I get enough intensity in the composite wavefront to knock off an electron? Kessler does not address this. He begins to talk of a resonance required. A resonance affected by the wave frequency and the mode that the electron is bouncing back and forth. But this too has problems. Why do higher frequencies work as well? Would there still be a resonance at frequency 1100, for example? I am not saying Kessler is on the wrong track here. I'm just not quite sure how when to resolve this final issue on cutoff frequency. So at this point, let's move back to Lamb and Scully. How did they look at this and resolve it? Well, Lamb and Scully simply evoked a quantized version of the atom with an electromagnetic wave falling upon it. They give the equation for this wave interacting with the atom and show that, to quote, it is clear that an electron will be raised to the kth excited state with appreciable probability only if the energy of this state is approximate to h nu. Then they plug in the known work function, phi, which exists for each metal, and show that h nu is equal to phi plus e, saying equation 17 can only be satisfied if h nu is greater than phi. That is, the energy received is greater than the work function. And we see that the energy dependence of the ejected photoelectrons obeys the Einstein relationship, even for a classical radiation field illuminating quantized atoms. The concept of a photon is not needed. They then derive the rate of emission, that is the number of electrons per second being emitted from the metal, or Q, as we've been discussing, gamma in their terms, and here's the expression for it. And they note, this rate, or Q, is proportional to the light intensity, as we've been saying, that is, to the classical notion of wave intensity or amplitude. And so what we've just done is pop the classical notion of intensity or amplitude out of the Einstein basket. And it's not proportional to the number of photons. Remember, for Doc, to increase intensity, just increase the number of photons. In my opinion, these are not compatible explanations. Wave intensity is equal to the number of photons. This is really true. Remember the picture we had. Low energy wave, just 3 photons, say. High energy, same frequency, well, we add more photons, just more photons. All the while embodying this strange Zen thing of a packet somehow involving a frequency. We witness Doc's incomprehension of this. It's completely nuts. That you can't have a wave thing or a photon thing. It doesn't make any sense. One has to give. So it seems quantum mechanics happens to work here with a C equals h nu, but something is deeply missing. Let's recall Wiki's statement way back, explaining away Lamb and Scully. That is, it's just wave-particle duality. That explains it. To which I said, smokescreen. Now I can see why. For wave-particle duality, you need particle-like behavior, like a double slit experiment where you're shooting particles through slits one by one, yet they exhibit wave behavior, an interference pattern. In the QM version of photoelectric effect, sending particles, photons, yes, but each photon is stripped of all wave properties. Each just has an E, an energy proportional to the frequency of and from some vibrator, but not a wave. There is no wave behavior to explain. I see no wave behavior in the entire QM story. To now appeal to duality is disingenuous. That is, after this complete denuding of the PE of all waves and trumpeting the end of the ether thereby, to say, oh, it still can be waves by duality, well, you be the judge of the intellectual honesty of this. So is the wave theory all that dead? Yes, there would certainly be a lot more to look at. We noted way back early that Lamb and Scully saw the Compton effect, spontaneous emission, black body, all needed quantization explanations, though we've looked at the black body and that seems a bit suspicious. So I wish we could be more definitive, but I am hardly a physicist, and I'm just going on my intuition that it's the wave theory that's important for Bergson, as I noted, and Bohm being important for Bergson. So we've done some cause for thought here, certainly, and it certainly seems all is not so settled, and that there are interesting questions. So next, looking at HOT, H-O-T, the higher order thought theory of consciousness. And down the road, I'm thinking of an update in LSD, since things are emerging on the biochemical basis that hadn't been understood before, and I think it could be interesting. So until then, signing off.